About 3 months ago, Intel released the Loihi neuromorphic chip. And about 2.5 months ago, they approached us, we're from Applied Brain Research, to see if we could make it do exciting things. So take this new piece of hardware and actually get it to do different kinds of AI algorithms, including things like recognizing keywords, controlling a robotic arm, and so on. And for us at ABR, this was incredibly exciting because what we do is build neuromorphic applications. And so what we were able to do over the last 2 months is start from sort of bare metal on a chip, programming, twiddling bits, and begin to build up what we call a back end. So taking our sort of software suite, which we currently have, which is called Nengo, in which we've developed a lot of our neuromorphic algorithms, and figure out how to map those algorithms right onto the hardware. So with an incredibly compressed time frame, we had about 8 engineers, most of whom are PhDs, working day and night to figure out how to take standard deep learning algorithms, convert them into a spiking algorithm, which is what Loihi is expecting, and then determine how we can actually map that right onto the chip to be able to recognize keywords or speech in real time. We also had a robotic arm that exhibits nonlinear adaptive control. And we had been running the algorithm in software just to show that spikes could do this kind of thing, that is, basically control an arm through a series of movements and let it learn dynamics in real time. And we figured out how to take Loihi, use the on-chip learning, and actually do the adaptation on the hardware. We found that this actually resulted in a huge amount of power savings, about 36-time improvement. We also mapped a deep neural network, which most people are familiar with, that does CIFAR10 onto the chip. And then we also got the chip to do some reinforcement learning. So across this sort of suite of examples, we began to build sort of the very first few steps towards what we think is a general back end, which will allow us to take the entire suite of algorithms that we can run on Nengo. With Nengo, we are actually able to run what is currently the world's largest brain simulation. It's called SPAWN. We're also able to build very big deep neural networks, convert them into a spiking version, and do sort of state-of-the-art image recognition, and a whole host of other kinds of applications that work on Nengo. And we're hopeful that over the next few months, we're able to take the backend that we've now sketched out and applied to these sort of 4 specific examples, and make it general enough that we can take the entire suite of applications that we've already developed for Nengo and map them right onto Loihi. In particular, the ones that are able to take advantage of the on-chip learning, which is a very unique aspect of Loihi that many of the algorithms that we've already developed in Nengo really rely on. We're showing the capabilities here of the adaptive controller that's been built by ABR and is running on the Loihi chip. And in order to sort of give a sense of exactly what's going on, it's helpful to compare sort of standard control, or actually it's a sort of state-of-the-art force controller with what we actually get when we include the adaptive hardware. So I'm going to begin by showing you what happens when we sort of take a standard arm and we move to a target. We've got a little Santa Claus, which is being recognized by a deep neural network. And you can see that the arm can move fairly accurately and sort of follow the target around. And the nice thing about this arm is it's actually fairly safe to interact with. And this is called a compliant arm because it's deciding just how much force it needs to get to its particular target. So this kind of safety is important when you're using robots. But it has one drawback, which is that if we, let's say, give it a tool or there's some other kind of disturbance to the dynamics of the arm, when it attempts to move to the target, it essentially makes a mistake. And that's because we've added a force which it's not accounting for anymore. Because we're trying to be safe, we don't want to sort of use more force than is necessary. But because we've added this additional weight, now it's struggling to try to, apply enough force to get to the target. And even if I help it out, it basically doesn't realize that it needs to maintain that amount of force. So we can compare and contrast this with an adaptive controller, where we have exactly the same kind of compliant controller, but in this case, we're going to sort of learn over time from the mistakes that are being made. And when it runs, it's now using a neural network. You can actually hear some spiking in the background. That's the network beginning to learn about the mistakes that it's making. And at the very beginning here, it has exactly the same controller we saw that was failing. But with a little bit of experience, it begins to learn that it needs to add additional force. You can see it's closer. With a few more reaches, it's going to begin to apply the amount of force that's necessary to actually get the arm now to the target, even though it's got this additional mass. And that entire process that we were showing there with the neural network learning over time to improve itself is running on the Loihi hardware, and all of the learning is actually going on the Loihi as well. And this is something very unique to this particular neuromorphic platform. In addition, we've made power measurements which show that it's actually 36 times more efficient to run this algorithm on the Loihi hardware compared to a CPU. So in this demonstration, we're showing how we can use the Loihi to do reinforcement learning. And this means that the system is essentially learning from its mistakes how to improve its performance. Here we've chosen a simple task of X's and O's. And what these graphs are showing is basically the improvement of the algorithm over time. So at the very beginning, when it doesn't know anything about X's and O's, it does very badly. And so it's actually losing most of the games. But over time, it's playing many, many games. And after it's played about 3,000 games, it's actually winning most of the time against another agent that it's playing. And so we can see what that looks like if we come over here and actually play against the computer ourselves. So this is the Nengo simulator, which is going to show us some neural spikes that are taken from the Loihi chip after training, doing all this training on the chip. And here we've got the tic-tac-toe board. And so we've had this at the conference for about 3 days now, and nobody's beaten it. So I'm probably not going to be any more successful. It's basically taken a turn, and it's waiting for me to take a turn. So I'll take a turn. And then we saw a couple of spikes. And those spikes are the Loihi deciding what its move should be, and then making that move happen on the board. So I'll take a turn. And then those spikes are it deciding what turn it wants to take. See, it blocked me. I can go wherever I want. And basically, it beat me because I did a very bad job. But in general, it's going to tie me. And if I make any mistakes, it's going to win. And what this is demonstrating is that the chip is able to take information about the state of the game, figure out what the next best move is based on all of the experience that it's had playing many, many games, and then perform as well as you can in this particular game, which is essentially always tying. In this demo, we're showing how we can use the Loihi chip to do something called keyword detection, which you're probably familiar with from using your phone, saying, "Hey Siri," or "OK Google." In this instance, instead of choosing one of those keywords, we chose the keyword aloha, because it's on a Loihi. So what we're seeing on the screen here, this again is the Nengo neural simulator. And we're showing all the audio activity that's coming in from the microphone near me. And then we're showing how the Loihi is processing that audio and whether it thinks I said aloha or not. So you can tell here it's just spitting out a bunch of garbage because I'm not saying anything that it recognizes, which is what we wanted. But if I say the keyword, then it should decide to accept my input. Aloha. So we see that it was accepted. You'll notice that it wasn't actually spelled correctly, and that's because it accepts some very small variations in spelling, because it's more likely to be aloha than any other word, and so it still accepted it. I can do it again. Aloha. Aloha. I got the right spelling that time. And on average, the accuracy that we're getting here is about 87%. The entire thing is running on this chip right here, which we need to have right near the computer because it's a very quick, real-time kind of processing that's going on. We did some power measurements earlier, and we showed that in this instance, the Loihi is 47 times more power efficient than running the same algorithm on the CPU. And so this makes it a sort of very natural application for things like phone or other kind of mobile devices, because we're doing this sort of deep neural network processing in a very efficient kind of way.
Hello, I'm Peter Suma, the co-CEO of Applied Brain Research. We're a startup out of the University of Waterloo, and we have the world's leading neuromorphic software development scientists and engineers. We build software that works like the human brain. And today, a very exciting development has occurred. Intel has released the Loihi chip. This chip on the hardware learns. It learns in ways very similar to the human brain. We collaborated with Intel in a period of just 2.5 months. We delivered all of the basic common AI algorithms delivered onto this spiking chip. What happens now? These chips process all of these leading AI algorithms, but they process them at 36 times or more less power and process them faster. Robots that respond in better time and faster response, more like a human. games that can be played very quickly with low power. This is going to enable a whole new generation of devices in the years to come. Cars that are smarter, that don't consume a lot of power, robots that can finally be untethered from their huge supercomputers that are required to power these deep learning algorithms. That's no longer out of our reach. We can now have mobile intelligent devices, cameras, televisions, appliances, et cetera. AI is coming, it's everywhere, but its potential needs to be embodied and realized. The Loihi chip gives us that platform. But for software to be developed, the world's software developers need to do that easily and quickly. And for that, we have the world's leading neuromorphic software development platform, Nengo, developed by Applied Brain Research, the partnership of the world's best chip company and the world's best neuromorphic software development company together, delivering to you the future of artificial intelligence embodied.